Okay. So, welcome back, everybody. So, this afternoon I will just give a talk about why we want to couple with waves, actually, and how, just in the general way, let's say, not so much in detail like in the practice this morning. So basically, I can change slides. Yeah. So wave coupling with wave, why? So here is a schematic from Fabrice Ardouin that illustrates all the processes around waves and why we want actually what waves induce both in the ocean, in the atmosphere, or in even the Earth's crust. And so there are many aspects that requires, or at least it could be useful to couple with waves. So first, let's start with the earthy interface. So basically with waves, surface is not flat. This is the first. Because waves can break, they can produce aerosols that can also have an impact on the earthy fluxes. And so they can have a strong impact both on the momentum and fluxes at the surface. And this can be parameterized, and it's generally parameterized when we are working with bulk formulations, but it's just considering wind speed and not actually the waves and the full spectrum of waves that we can have. Also, these waves and the fact that the surface is not flat is used actually for a lot of applications, notably in remote sensing. It is a way that we can retrieve surface height, wave height, of course, but also water level elevation, water or the ocean surface elevation, also the currents or the winds. So all these can be retrieved by satellite thanks to waves. And sometimes we want to remove the part of the waves, but the fact that the wave is modifying the radar signal makes that possible to measure actually all these parameters. Then the waves have strong impact also on the ocean circulation and mixing. So there is the well-known Stokes drift, I will speak about a bit later, that the fact that the waves can induce a drift at the surface and also under the surface. The waves, they also generate mixing while they break. They can also generate what we call the Langmuir circulation, and I will explain this a bit later also. And when going close to the shore, they can have strong interaction first with the bottom, but also with the coastlines. And near the shore, clearly, the circulation is mostly driven by the waves. So there are many applications in which these kind of things need to be considered, typically the drifting of objects or pollutants, and also the biology, because when you change the mixing and when you change all the things, and we were talking about that, I think, a few days before, that it can change really the biology and the way that larvae or stuff are dispersed around. Then there are interactions between the waves and the sea ice. The waves can actually propagate through sea ice. So this is something that can be accounted for. We won't talk that much about that because it's clearly not my area of expertise, but there are plenty of work on that. And as said by Andres a few days before, all these waves can be filled like microseasons in the crust of the Earth, and it's known as the Earth hum. And basically, people working on geology that generally want to remove that, but it can be censored actually. And regarding engineering, waves are quite important, and there are generally first studied for engineering purpose, like offshore platform or nearshore structure, like structures that can protect the coastal area and stuff like that. And also for maritime transport, it can be quite important. So we have waves-wind interaction, so that and feedback between those. So first, surface waves, what we're talking about, they are generated by the wind. So basically, there is first this interaction that is necessary. Then they change the surface roughness, and so they can modify the wind stress and then the momentum and heat fluxes. There is also an interaction because waves, we have let's say, a panoply of waves, like small and short wind waves up to long swell. And when the swell is traveling faster than the wind, it can also have feedback towards the atmosphere. Then waves can also move part of the energy input to the ocean. When we neglect waves, we consider that we have a wind stress and it's directly impacting the ocean underneath. But if part of this wind stress is first carried by waves and then released somewhere else, we can have a change, let's say, of part of the energy that is moved from one place to another. Then we have current and waves interaction. So waves can be influenced by currents. They can also be influenced by the water level and the bottom roughness when we are going close to the shore. And waves can also generate currents and then modify the water levels. They can modify the bottom roughness. They can even modify the sediment places and so modify the morphodynamics close to the coast. They also enhance upper ocean mixing, and they can break the ice, push it, but also propagate through the ice. So these are all these processes that should be accounted if you want to account for waves. So first I will develop a bit more what the waves atmosphere interaction, even if it's not the main purpose of what we will do tomorrow, but I think there are really things that matters even when you want to couple waves and ocean, regarding the fact that waves are changing the surface condition, and because of that, they have an importance even in the case of ocean wave coupling only, because you're changing the surface stress. So this is a slide just saying that waves are generated by the wind. We have said that in wave watch, for example, there are many different possibilities for source term, for example, and this is partly because at the moment, even now, we don't really know how to create waves from a flat ocean. There are still questions about theory about that. We know how to grow waves when we already have small little waves, but how to create waves from a very flat ocean, purely flat, is still a matter of research. And the way it grows, if we start with this wavy surface, is the fact that the wind and one part of the waves where the surface is already descending. So if you imagine there is a point here at the surface of the waves, it was there. And then when the wave passes, it descends. And when the next phase arrives, it's going up. And so on this side, on the left side here on the waves, the wind is just compressed. And so it gives a pressure force to the waves where it's already descending. So it's increased this motion. And on the other side, as the isolines here of the wind are more sparse, you can see that the pressure force is in this direction, and where the surface is already moving upward. So you're amplifying this wave motion, and that way you make the wave growth. So then we can consider that there are many, I won't go into detail in the equations, but this was just to show you a form of the energy rate by surface unit transfer from the wind to the waves. And if you look at this equation, you can see that it is positive when the waves travel in the wind direction, and it's negative when the waves travel in the opposite wind direction, and it's zero for the waves traveling in normal direction to the wind. So this transfer, it exists only if the wind speed is greater than the phase speed of the waves, and otherwise the wind will pump energy from the wave. I have a slide on that a bit further. Most of the time, wind is faster than the waves that are underneath, and it makes the wave grow. So the impact of the waves on the acid fluxes are generally parametrized. So here you have the wind stress formulation, that is the product of the variation of U and W. And in a model, generally, we're using bulk formulations that consider that these turbulent motions can be parameterized through a drag coefficient, CD, and the wind speed. And this drag coefficient, it's represented on the right-hand side here. most of the time it's taken as a function of the wind speed. So we're considering that higher the wind speed, higher the waves, and rougher is the surface. Okay? But here we consider that waves are really linearly related to the wind speed. And roughness is linearly, or with this relation related to the wind speed. But it is known that actually, for one given wind speed, for example, here 15 meters per second, we can have various drag coefficients because of the waves, because we can have various kinds of waves for a given wind speed. And so to represent this variability, you need to consider the sea state actually. And so there were different parameterizations that were tried to make this happen. So either based on the wave age, because it was shown that generally young waves are rougher than old waves, let's say. So there are different existing parameterization, but I will show you that definitely it's still state-of-the-art problem, because this picture, I like it really, it's the state-of-the-art of the parameterization existing for the drag coefficient as a function of wind speed. And you can see that definitely there are many. Okay, and especially when going to high wind speed. So you can see this one, which is very stronger at high wind speed than the others, was taken in a tropical cyclone, in a specific part of a tropical cyclone, because in tropical cyclones, sometimes the surface is rougher, and sometimes it's not. So it really depends on the region of the tropical cyclone you are on. So you can have at the same time, in the same event, let's say this drag coefficient and this drag coefficient. So really, it's something that is work is still needed in this area for sure. Then, besides the momentum flux, there are also impact of the waves on the heat flux through the same consideration as the momentum first, but also through the sea spray that can be emitted by waves when they break, that can change really the rate of heat exchange between the ocean and the atmosphere. Because you can imagine that evaporating a really small droplet is easier than evaporating from the surface of the ocean. And because of that, this is still a bigger area of research, I would say, because it's very difficult to measure this kind of things. And so there are many existing parameterization, but here is an example just of transfer coefficient of heat and momentum. In red and blue, it's for a simulation with sea spray, and green and black without sea spray, and you can see that they are very, very, very different. Then the last thing on the momentum flux is what I discussed a bit earlier, the swell feedback. So if the waves start moving faster than the wind, then it can bring back momentum to the atmosphere. And actually, in a paper of Fabrice in 2009, they showed that swell dissipation is observed across the ocean. So without breaking, let's say, swell dissipation. And it's necessary to consider this dissipation to have accurate wave forecast. And to do so, they decided to put a term that removes part of this energy of the swell, so that acts as swell dissipation. And that's why there is this very complex ST4 parameterization from Fabrice in Rewatch, with a lot of coefficients in there. And then there were different papers before and after this paper that shows that we can have wind stress reversal over swell. We can have a jet that is created in the low-level winds at a low level. And here is a schematic that I took from another paper, but I think it's well representing that usually we consider that we have a log profile of the wind above the ocean. And when you start having really big waves and long swell, you can start to have really a modification of this wind profile above the ocean. And this is generally not considered in the model because it's difficult to do. We generally stick with a log wind profile. But there are now more and more works that have tried to implement parameterization for this kind of different profile in the low level due to waves. This is something that at the moment in the coupling that we are doing, we are not doing that, but we will. It's a really ongoing work that we will try to have something better results for that. Obviously, this swell feedback is only happening. Here is a graph that shows that with the drag coefficient of the function of U10, when you are going basically, so this negative drag at low wind speed, of course, because when the wind is faster, the waves cannot be as fast as the wind then. So now let's move to wave-ocean coupling. So besides the fact that this wind stress will influence also the ocean, this change in the wind stress. So there are strong two-way interactions between the waves and the currents. First, I will talk a bit about the current effect on the waves. So when you have a current gradient that can be represented there, you're changing the velocity of the waves that are propagating on top of this current. And so if you are changing the phase velocity along a given section there, because of the energy conservation of the wave flux, you will have a change in amplitude of the waves, and you will have the waves will start turning. So this is typically refraction of waves due to currents. Then you can have, as you have also a change in the group speed, you will have also what is named shoaling. So it's a modification of the amplitude associated also to energy flux conservation. And here are some illustrations of that. So basically, the first picture on the left top side is the mean significant wave height gradient. And what do you see in this significant wave height gradients? Definitely you see currents, main oceanic currents. So you can see the Gulf Stream, you can see the Kuroshio, you can see the Algulas currents. So basically, the change in the wave height is associated to currents. And this is from satellite observations. And underneath, it's a mean geostrophic current vorticity, where you definitely see currents. And here is a zoom on the Algulas region, for example. And you can see on the right current or vorticity, and on the left-hand side, you can see significant wave height. And definitely, there is a strong correlation in the spatial pattern. And on the right bottom, you can see that in black, you have satellite data, so altimetric data. In red, you have wave simulation with WaveWatch without accounting for the currents. So you can see that the general evolution of the wave height is okay, but the high resolution in space evolution or carrying frequency of the wave height is not. And when you add currents in the model, so you take into account the effect of the current on the wave height, you can see that it is much better resolved compared to observation. So if you want to really resolve this kind of pattern associated to the refraction of the waves over currents, you need to have currents. Then, on the other side, the waves can generate currents. So basically, if there are waves on a surface that is on an ocean that is not moving, a particle that would be at the top of the wave will do this circular motion as the waves pass, okay? You can imagine. But if there is a current, an underlying current under the waves, this motion won't be circular anymore, but it will be elliptical like this, and then the particle is moving forward with the current, okay? And this is a Stokes drift. So this is a drift associated to the fact that you have waves above a current. And associated to this drift, there is a transport that is generated, and this transport is compensated because everything tried to be balanced in general. And so there is a Stokes-Coriolis transport that is opposed to this Stokes transport that is starting to be generated. But as we are never at the perfect equilibrium, a balanced situation, there is still a Stokes transport that is residual when you have young waves. Then the current can induce can induce so this drift. And here is an illustration of what you can have for particle advection. Here it was for the Sargassum drift in the Atlantic Ocean. And it's a paper from Julien Joanneau, and it really showed that there is a complete difference when you account or not for SOx drift in this drift of particles or here of algae in the ocean. And here are some numbers. So it's really depends if you have old or young waves, so waves that are just being generated that are in less equilibrium with the ocean and with the SOx Coriolis transport that is trying to balance this SOx transport, or if you have long and old swell where the balance is more or less reached. So here you have in red you have younger wind sea where it's not balanced at all, so you have strong drift at the surface. And then when you have old swell, you have less drift at the surface, but you can see that on the transport, you can find a transport that is residual. Then there is mixing injection due to wave breaking, actually, and wave turbulence interactions. And here is just a profile, dimensionless profile, actually, of the kinetic energy injection that is due to breaking in red and in black to the wave current in turbulence interaction, the wave turbulence interaction. And this is just the same but in a log scale. So this has an impact on the mixing, then on the mixed layer depth, for instance, or on biological tracers in general, and eventually biological traces. There is also another impact that is related to mixing is the laminar circulation. So as the waves generate this SOx drift, it tends to stretch until the vorticity near the surface. And in balance to that, the production of this vorticity is balanced by vertical motion, so downward and upward, creating these cells. So there are of relatively small scales, and generally they can be parametrized in models, and there are different kind of parametrization for that. So here it's a plot showing for the Southern Ocean, I think, the evolution of the mixed layer depth when you account for these different terms in a coupled model. So it was performed with a NEMO WaveWatch 3 coupled model. And you can see that in black, it's the observation from the Argo floats. And in red, let's say it's one of the full coupled simulations. So we're quite happy of the distribution of the mixed layer depth compared to Argo floats. And when you start, and in blue, it's without happening with the waves. So we're not happy. Too few deep mixed layer depths, okay? And when you start accounting for waves, you can see that all of the terms have an impact. So in gray, you have the impact of the change in the wind stress due to waves. In light gray, you have the impact of the SOx drift. In yellow, you have the impact of the change in kinetic energy provided by wave breaking. And in green, you have all the terms accounting for one Langmuir parametrization and the red with another Langmuir self-parametrization. So you can see that we have all these different things. And it's quite important, you can imagine.
So that was a PDF?
Yes, it's a PDF of the mixed layer depth.
Why is probability?
Yes, it's probability densities on the y-axis, exactly. So you have too few deep mixed layer depths when you are not coupling, and too many shallow mixed layer depths in the Austral Ocean, in the Southern Ocean. And so finally, near the shore, so I've said that near the shore, the circulation is driven by the waves. It's quite important. So this schematic can summarize a bit all what you can have. So you can have, when the waves start filling the bottom, you can see that besides this movement forward motion of the water due to waves, you also have a change in the shape of the orbital motion due to the filling of the bottom. You can also have strong interaction with the bathymetry. and you have different currents that can be generated. So basically, you have change also in the water level, let's say. So the most usual thing that can be considered at a medium resolution is wave setup. So it's the fact that when you are in the breaking zone, wave height rapidly decrease. And because of that, there is a resulting pressure gradient towards the shore. And in compensation of this pressure gradient, you have a setup that is observed in the waves. Okay. And so you change the water level due to wave breaking coming close to the shore. There is also the impact of infragravity waves. So infragravity waves is the fact that waves travel in groups, and sometimes you have an interaction between the different wave groups, and you can have this oscillation of the water level and mean water level due to the effect of these groups. And when you're at the beach, basically, you are looking at the shore and you put your towel somewhere, not so far from the water level, and every 15 minutes, 10, 15 minutes, you have a wave that can reach your towel. And then not. It's not tide, it's infragravity waves typically. And finally, there is wave run-up. So this is really the motion of the waves up to the shore, specifically of each individual waves. Then, at a scale more of the beach in general, when waves are not completely normal to the shore, which is most of the time the case, so waves will generate a drift and a current that is along shore then. So that's why you can generate this sand tongue, let's say, I don't know how it can be, because you have this longshore drift that is most of the time the same, and then it's pushing the sand, and you're creating these things like a new tongue of sand due to this longshore transport. You also have a cross-shore circulation. So there is indeed the onshore current due to waves, so the Stokes drift. You also have the impact of the bottom streaming, so the wave stress in the wave bottom boundary layer, and start feeling the bathymetry. And you have what's named the rollers, so it's a fraction of wave energy that is converted into rollers that propagates toward the shoreline. So part of the energy keep propagating. And in response to this transport towards the shore, you need to have a balance. And so you have an offshore direct current that is named the undertow. So in this section, you can see that close to the surface, we have a direction of the current that is toward the shore. And in the bottom, the direction of the current is towards offshore. And finally, due to the non-uniform bathymetry, so typically sandbars and stuff like that, you can have the creation of what is named rip currents. So this current where you have transport associated waves on top of the bar, and then the change in vorticity, the limit of the bar makes this current that goes outside, and it is very dangerous for swimmers, actually. So many things to consider when you're in the nearshore zone, and if you don't have the waves in the nearshore zone, you will not properly simulating the circulation.
So, as a rule of thumb, I've heard that if the depth is less than 10 meters, wave energy dominates. No, will be that.
Yeah, I think it depends on the height of the waves and of the wavelengths. Because the important is the wavelengths most of the time.
But it can be more than that. It can be in deeper areas.
It can be when you start feeling this orbital motion of the wave, there's a strong impact. If you have very long waves, you can have impact of the waves up dominating a long, but really strongly impacting the circulation.
In area depths of how much?
It really depends on the wave field, I would say. But you can feel the waves at some very big depths. It's very energetic and long waves too.
Big is 50 meters?
No, it's the wavelength that accounts most of the time, more than the height. So now we go back to how coupling, not as this morning, but more in the general picture. So basically waves are this whole thing that we can see when we are at the beach. And there are very small scale. So basically, if we want to look at the wave climate, it's not possible to model this kind of waves because it would require to have a very, very, very small resolution that we can afford at a global scale. And because of that, and also it's very nonlinear, it's very complicated. And so because of that, we are using spectral models in general that model actually the spectrum of the waves. So it's not modeling individual wave, but the spectrum of the wave. And it's just transferring the energy of the spectrum either in between frequency and direction or as a source term or as dissipation. Okay, and the interest of the spectrum is obviously less complicated, but also it's much more linear, let's say. So it's much less complicated than a true wave surface. And this is generally the way that we use to model waves at a large scale or even coastal scale, actually, most of the time. We will see in the end that we can do some different stuff when you are really, really near shore, but it's another story. So